Okay, so what I wanted to do in this video now is go through the 2 gas questions that I gave you. Now, they were pre-questions that I got from previous years. They weren't examinations on examinations.ie, but define an ideal gas. So an ideal gas is one that obeys all of the assumptions of the kinetic theory of gases under all conditions of temperature and pressure. 2 reasons why real gases might deviate from ideal behaviour. Well, remember the assumptions. We went through the assumptions to the kinetic theory of gases, and one of the 2 we said we would focus on was that the first one that it said is that they don't have a volume. Now, gases do have a volume, okay? So they do have a volume. So to say that their volume is negligible isn't true, okay? And the other one then that we said we'd focus in on is that there are forces of attraction between gases, okay? So that's how another reason why real gases will deviate, because they will attract to each other, even if they're not polar molecules like, say, hydrogen. So if I have one hydrogen molecule here and another hydrogen molecule there, they're not polar, but they'll still attract through van der Waals. So you do have, so the 2 reasons we'll stick with is we do have attractive and repulsive forces between the molecules of the gas, and the volume is not negligible. Gases do take up a certain amount of space. So they're the 2 reasons why real gases will deviate. Now, under what conditions of temperature would real gases come closest? So they'll come closest under low pressure and high temperature. Now, why is that? So at low pressure, then they're spaced out from each other. And if the temperature is high, they've got lots of energy, so they're moving quickly. So if they're moving quickly and they're spaced out, then the forces of attraction, they don't set up forces of attraction as easily if they're very spaced and if they're moving really quickly. And also, in context to the size of the container, if they're widely spaced, their volume may not need, it may not seem so significant, if you like. So the volume may be negligible in context to the space that the gas actually has. So you're just asked there, low pressure, high temperature. Now, for the calculation, we're going to use PV equals N or T. But remember, the hardest part of this formula is that you need to fill in the quantities in certain units. So you have to have volume in meters cubed, okay? Now, if you're given volume in centimeters cubed, then what you have to do, what you have to do is you have to multiply by 10 to the minus 6. So you're going to have to remember these. Centimeters cubed multiplied by 10 to the minus 6. If you're given volume in litres, you must multiply by 10 to the minus 3. And remember, the other thing is your pressure has to be in pascals. So if you're given kilopascals, kilos 1,000, so multiply by 1,000 to change to pascals, okay? So just you need to remember those quantities there. Now, in this question here, you're asked to calculate the MR. You're not told what the gas is, so your unknown is N. So the first thing is to manipulate the formula to get in on its own. Now, if you need in on its own, you need to divide that by RT to cancel that. So you'll also divide the other side of the equation by RT. So N equals PV all over RT. So we'll fill it in now next. So N equals P is the pressure. It told you in the question that the pressure was 1 by 10 to the power 5. Oh, now, they used newtons per square metre. It's the very same as pascals. So newtons per square metre, very same as pascals. So you just write it down as 1 by 10 to the power 5. Okay, now the volume was given to you in centimetres cubed. So you have to multiply that by 10 to the minus 6. Okay, the R, you were given that in the front of the paper is 8.3. Now, some of you might have used 8.31 because I didn't tell you the R. So it doesn't, if your answer is slightly different, that's the reason. And 27 degrees Celsius, you can't fill in degrees Celsius, you need Kelvin. And remember, 27 degrees, you plus 273 to that to change to Kelvin. So you're going to get 300 there when you do that. N then works out at 0.00675 moles. Okay? Now, just to clear that there now. So 0.00675 moles is the number of moles of gas you had. That, you were told in the question that has a mass of 0.3 grams. So what would the mass of 1 mole be, which is what you're asked to calculate? You have to divide this side, okay? And then you'd also have to divide that side by 0.0675. And when you do that, then you're getting 44.44 grams, but they asked you for the nearest whole number, so it's 44 grams, okay? Now, in part B of that then, this is a stoichiometry style one. So remember when we were doing these, we had very clear steps. So number of moles and then ratio. So the first thing is number of moles. Now you're told the grams of the manganese dioxide, right? You're told that was 4.35 grams. When you work out the MR of that and show the workings out of the MRs, then you get 87 when you do that, 0.05 moles of the manganese dioxide. Okay, next step now is your ratio, and you're asked how many moles of HCl. Now look at the ratio. The ratio is 1:4 between manganese dioxide and HCl. So multiply by 4. So if you have 0.05 moles of the manganese dioxide, 4 times the HCl is required. So 0.2 moles of HCl is your answer there. Okay? Now, in the next part then, in part 3, you're asked to calculate the number of molecules of water that would be produced. Now, what's your ratio? So you go back to your ratio. Okay, now I'm just going to put in here that I have already calculated that this is the moles of the manganese dioxide. So what is the ratio between manganese dioxide and water? 1:2. Look at the water there, 1:2. So if you have 0.05 moles of the manganese dioxide, then you're going to have 0.1 moles of water. But go back and read your question. You asked for number of molecules. So you'll have to multiply that by 6 by 10 to the 23. So when you do that, you get 6 by 10 to the 22 molecules of water. Okay? And then finally, you're asked how many atoms of hydrogen. Now, lads, we did these before. 1 molecule of H2O contains 2 atoms of hydrogen. Look, so if you draw a molecule of H2O, HOH, look, you're drawing 2 hydrogens. So for every molecule of water, you have 2 atoms of hydrogens. Remember that a molecule is a group of atoms. So in this number of molecules of water, you're going to have times 2 the number of atoms of hydrogen. So your total answer then, or your answer at the end, is 20, that's a 23 atoms of hydrogen. Okay, now in the next question that you had there, the gas question, I just want to use a photo here, look, of the apparatus from your revision book to speed it up slightly. You're asked to name a liquid that was suitable. We used propanone, okay, or acetone, but propanone is the correct term. Then you're asked to draw a label diagram. So you would be drawing the middle diagram there. Let me mark this up for a second. So you'd be drawing this sort of diagram here, all right? So and label everything. So you'd be drawing your hot plate, your beaker of boiling water, your conical flask with the pinhole, the elastic band, the thermometer, everything, okay? So that's how, so you'd be labeling that. And then they asked you to describe in part C how the mass of the vapor was determined. So you would have to give these steps. So you would have to say that you would find the mass using an electronic balance, find the mass of a dry conical flask, an elastic band, and the aluminium foil. Then you would say that you'd add your acetone and that you would evaporate fully, okay, evaporate fully. And look, the excess vapor comes out through the pinhole, remember, so that the whole flask is full of vapor. Then you allow it to cool, and when it cools, the vapor is going to condense inside the flask. Dry the outside. You must say that you dry the outside of the flask, because otherwise you're going to include the mass of the water on the outside. And you reweigh then to find the mass of the liquid, the flask, the elastic band, and the foil. And then say by subtraction, okay, you calculate the mass of the condensed liquid. So that's the vapor. They're drawing the pink vapor there, so you see the flask is full. When that vapor is allowed to condense, that's the mass of liquid, condensed liquid from the vapor that once filled the flask. That's what you're getting the mass of. Okay? Now, then for part 2, then it asks you the volume of the vapor. Well, the vapor filled the conical flask. So if you fill up the conical flask with water to the brim and then transfer it to a graduated cylinder without spilling, then you'll be able to measure the volume from the cylinder. And then finally, how can the pressure be measured? You use a barometer. Okay, so just go back to the show me board now for the calculation. Right, so same formula, PV equals N or T. Manipulate the formula to get number of moles on its own. So N is equal to PV all over RT. Filling it in there, you were told that pressure was already in pascals, so you just fill in the pascal pressure there. Now the problem was, all right, look, that was cubic centimeters, 84.5 cubic centimeters, so you multiply by 10 to the minus 6. They used 8.3 for the for the constant. You'll be given that in the question. And 100 degrees add to 273, so you're going to get 373. And your number of moles then works out at moles. Okay, now they told you in the question that number of moles has a mass of 0.12 grams. So what would 1 mole, that's moles, what would 1 mole have a mass of? Divide both sides, okay, by 0.3, and you're going to get 46.3 grams as your answer, okay? And then finally, why is this method not suitable for non-volatile? Well, non-volatile liquids won't evaporate easily. For this method, you need to use liquids that will have a low boiling point. They're easy to evaporate. They evaporate easily. Okay, that's the answer to that. They don't evaporate easily if they're not volatile. And then they didn't ask you there, but sometimes they might ask you, how would you calculate the MR of non-volatile liquids? And your answer there is that you'd use the mass spec. Remember, we came across that when the school. So the mass spec is how we measure the molecular masses of non-volatile liquids. Okay, thank you.